Let's run through complete solutions to multiple choice problems 19 to 24, non-calculator, on the released 2012 AP Calculus AB exam. There's some really good stuff in here that will help you practice the chain rule and the product rule, and also help you figure out how to interpret and work with the derivatives. I personally think the toughest problem is problem 20. It involves taking the derivative of an inverse function. People tend to forget how to work with inverse functions, so keep a lookout there. But apart from that, let's dive in. In question 19, we're given a function and we're asked to find where its tangents have slope equal to 1/2. So when we see tangent and slope, I always want to immediately think derivative. So we need to find f prime of x and actually solve when it's equal to 1/2. So first things first, let's figure out f prime of x. Now, the rule for this function is a quotient. It's a numerator over a denominator. So we're going to need to use the quotient rule. Now, you'll probably have your own way of remembering the quotient rule, maybe low d high minus high d low over low squared, or maybe in terms of u and v. So if u is the numerator and v is the denominator, we have vu prime minus uv prime all over v squared. So let's plug in here values for u, v, u prime, v prime. So v is just x plus 2. The derivative of u is 1. Subtract u times the derivative of v prime, or the derivative of v rather, that's just 1. And that's all going to be over v squared. So because I'm going to be working with this algebraically, it probably makes sense to tidy it up a little bit. So you can see in the numerator, my x's will cancel because I'm subtracting, and then I get 2 minus 1. So what I end up with is 1 over x plus 2 all squared. So I've got my expression for f prime. Now let's solve when that's going to be equal to 1/2. 1 over x plus 2 all squared. I want that to equal 1/2. Let's cross multiply. So I'll end up with 2 equals x plus 2 all squared. Let's expand out those brackets. So I'll get x squared plus 4x plus 2. Again, I can subtract 2 from both sides to get 0 on the left-hand side. And now I can factor that right-hand side as x times x plus 4. And using the zero product property, that tells me x is either going to be 0 or negative 4. So if I look at my answer choices, you can see only one of them has x coordinates at 0 and at negative 4. And that is answer choice C. Now we're pushed for time on the AP exam, right? So we're probably maybe going to move on there, trust our work is correct. But there is this little niggle here. There might be no such points. Maybe I made a mistake along the way. So if we have time, if we're not sure of our work, we can check that the y coordinates match up. Okay, so let's check that f of 0 indeed gives me the y coordinate that I'm looking for, 0. So indeed I do get 0 over 0 plus 2 equals 0. And f of negative 4, if I plug that into the rule for f, I'll get negative 4 over negative 4 plus 2, which, if I figure it out, does indeed give me the 2. Nice. Problem 20 is the one that I flagged at the start as kind of tricky because it involves inverse functions. And maybe that's just revealing about myself that I always forget the formula for the derivative of an inverse function. Maybe you don't, and that's awesome. Whenever I do forget, though, I'm always able to recover it by remembering the definition of inverse functions. So we're told that f has the rule 2x plus 1 all cubed, and g is the inverse of that, and I'm given some information about the value of f at 0. Okay, so by definition, we know that f of g of x, if f and g are inverses, that should just be sending me straight back to x. Okay. So we can see this with the example they've given us. If I take the value of 0 and plug it into f, the output that I get is 1. If g is the inverse of f, it had better send 1 straight back to g, because I want that inverse to be undoing what f did in the first place. Okay. So this formula here is really just the definition of what it means to be an inverse function. I never forget that, at least. So what I can do to this equation is differentiate both sides with respect to x. So if I do that, okay, the right-hand side, x just differentiates to 1. That's nice and easy. That left-hand side is a composite function, so I can differentiate it using the chain rule. So the chain rule tells me I take the derivative of the outer function f, evaluated at the inner function, and I multiply it by the derivative of the inner function g, evaluated at x. So you can see here, if I rearrange this, g prime of x, the quantity I want to figure out when x is 1, is 1 over f prime evaluated at g of x. So I'm not interested in this in general, I just want to know what happens when x is 1. So let's figure out here, what do I need to know? Well, I need to know g of 1. But I already figured that out, right? From my little diagram up here. G of 1 gets sent straight back to 0 because we're undoing what f did. The other piece I need to know is f prime. Well, I have the rule for f, so I can take its derivative. So let's find f prime of x using this rule. Well, it's also a composite function, so I'm going to have to use the chain rule. The 3 comes down as a power, and I reduce it by 1. I leave the 2x plus 1 alone, but the chain rule makes me multiply by the derivative of that inner function, which in this case is 2. Great. Okay, so now I can substitute in using these quantities. So g prime of 1 is equal to 1 over f prime evaluated at g of 1, which I already worked out was 0. So I can write this as 3 times 0 plus 1 squared times 2. If I do the math there, I'll get 1/6. Answer D. Now we could have approached this a different way. We could have worked directly with the rule for f to write down a formula for g of x. Okay, if we're confident with rearranging to find inverse functions, we could have found a genuine formula for g in terms of x. It would have involved cube roots, that sort of thing. And then we could take the derivative of that formula using our standard techniques. It really just depends on what you prefer. Question 21 is asking us about horizontal asymptotes. It wants us to find which function has a horizontal asymptote at y equals 5. Now, when you see horizontal asymptote, what I want you to think is, you're really being asked, what is the y-coordinate approaching as x approaches infinity or negative infinity? So what is this function outputting in the long run as x gets really, really positive or really, really negative? And we can just run through these examples to figure out which one has that behavior, a horizontal asymptote at y equals 5. So if we look at our option A, sine 5x all over 5, well, the numerator there, no matter what x is, no matter how big x gets, that numerator is sandwiched between plus and minus 1. That's what sine functions output. But the denominator is getting larger and larger and larger as x gets larger and larger and larger. So we're taking a quantity stuck between 1 and minus 1, and we're dividing it by huge, huge numbers. So that forces that quantity to 0. So there is a horizontal asymptote for this function, but it's at y equals 0, not at y equals 5. What about b? Well, b is an even more straightforward function, y equals 5x. As x gets really big, 5x gets even bigger. It's 5 times bigger. So this quantity is going to approach infinity or negative infinity as x approaches plus or minus infinity. Okay, it just grows without bound. So it can't be b. For a similar reason as in part A, option A, y equals 1 over 5x, that numerator is constant, it's 1. That denominator is getting bigger and bigger and bigger. Subtracting 5 isn't really making a dent in it when x is some huge number of zeros after 1 or whatever, okay? So that is also going to approach 0. So it has a vertical asymptote, but it doesn't have the correct vertical asymptote. So our head-to-head final is option D or option E. These are both rational functions, polynomial over polynomial. And you might remember that the long-term behavior of those, the horizontal asymptotes of rational functions, have something to do with the ratio of the coefficients of the leading terms of the numerator and the denominator. If you remember that, great, apply it. I want to show you what to do if you forget. I want you to get comfortable working with these quantities directly. So the key thing you want to use here is divide top and bottom by the same quantity. And the quantity you're going to divide by is the highest power of x that you see. So in answer choice D, the highest power of x that I see is x. So if I divide by x over x, that's really just dividing by 1, so I'm not doing anything. I'm just rewriting the function. And when I do that, I get the numerator becomes 5, and dividing term by term in the denominator, I get 1 over x minus 1. Now this is a helpful thing to do because in this form, I see that as x gets bigger and bigger and bigger, the 1 over x gets smaller and smaller and smaller, closer and closer to 0. I'm dividing 1 by a larger and larger number. So this is going to tend towards 5 over 0 minus 1, because the 5 and the minus 1 aren't changing. So if I simplify that, that gives me minus 5 as my horizontal asymptote, y equals minus 5. So we should probably check part E, but if we're short on time on the AP exam and we're confident in our work so far, we could just say process of elimination, it has to be E. But let's check. Okay, this is again a rational function, so I'm going to divide top and bottom by the highest power of x that I see. In this case, it's x squared. Dividing by 1 doesn't change anything, it just rewrites the function for me. So going term by term, the numerator becomes 20 minus 1 over x. The denominator becomes 1 over x squared plus 4. Again, the only x's are now appearing in denominators of simple fractions. So that will tend towards 20 minus 0 over 0 plus 4. If I simplify that, I get plus 5, which is what I want to see. So E is my correct answer. The beauty of these last two is you're able to rewrite the function so that only place that x appears is in the bottom of fractions, the denominators, and you know exactly what happens when you've got a constant over a power of x. Problem 22 is my runner-up for toughest problem on this set because it's sneaky. So keep an eye out. It's asking us to find the absolute maximum value achieved by this function, f of x. So whenever you see absolute maximum, I want you to think you need to solve the derivative f prime of x is equal to 0 or does not exist. Okay, that is when, for nice continuous functions, our absolute max values or min values have to appear. So let's find f prime. Well, again, we have a quotient rule here. So I can use my formula, u over v, vu prime minus uv prime all over v squared. So I have v or rather x times the derivative of ln of x, 1 over x, subtract ln of x times the derivative of x, that's 1, and my denominator just gets squared. Again, since I'm working with this algebraically, let's tidy this up a little bit. So my x over x will cancel. So I'll get 1 minus ln x over x squared. Now, this rule for f prime exists for every x in the domain of the function I started with. You might be worried about dividing by 0 or taking log of a negative value, but you can see I wasn't allowed to do either of those things in the original function. So this derivative will always exist. So the only thing I need to worry about is when it is equal to 0. So let's solve this expression, 1 minus ln of x over x squared equals 0. That can only happen if the numerator is 0. And if I rearrange this, I get ln of x equals 1, which, unpacking the log notation, that just tells me that x is e. So we're done, right? No, we're not done. This isn't one of our answers. X equals e is not one of our answers. So maybe we're tempted to say e, f has no maximum value, because something went wrong along the way. But remember, it was the absolute maximum value. Okay. It's also possible that this is telling me about a minimum value this function has. So if we really want to chase this down and understand that our answer is fully correct, we should draw a little graph of the function and make sure that we're happy with what we see. So we know that at x equals e, there's supposed to be a horizontal tangent line. That's where f prime was 0. So I don't know where that point is, but let's just put it there, say. And I know that I have my horizontal tangent line. Now, if I look at the value, the sign of f prime when x is less than e, okay? So for example, I could take x could be 1, okay? In that instance, looking at my rule for f prime, because log of 1 is 0, f prime will be positive. And when a derivative is positive, that tells you that the function is increasing. So I'm not really sure what's happening, but I know that my function is increasing. When x is less than e, let's double check on the other side. When x is greater than e, so an example we could take might be, with a calculator we could pick anything, but here it might make sense to pick e squared, because the log of e squared is 2. When I substitute e squared into my formula for f prime, I get that f prime is negative. And when a derivative is negative, that tells us the original function is decreasing. So I get my nice horizontal tangent at x equals e, and then I decrease. So it truly is a maximum value occurring at x equals e, but x equals e is not the maximum value. It's where it occurs. Value is output of function. So what I need to know is what y coordinate does the maximum value occur at. Okay, when x equals e, what is y? So we need to find f when I plug in e. So I get ln of e over e, just using the rule they gave us. And because ln of e is 1, I get 1 over e. So my answer is B. Now, problem 23, I think, is trying to make you a little uncomfortable and check how confident you are seeing terms in slightly unfamiliar places. It's talking about differential equations, so you might be thinking about trying to solve these. Certainly, they all look kind of separable, so you could solve them. But it's checking, do you know what it means to grow linearly and what that looks like when we write it down as a differential equation? Okay, so the key thing I want to focus on here is linear growth. So this function p, we want to grow linearly. We want it to be a linear function. So we want p of t equals some linear function. And we know that a linear function looks like ax plus b, where a and b are constants. Okay. So now all of a sudden, all of my answer choices are just asking me, hey, what is dp by dt, that derivative? And I can take that derivative really easily. When I take the derivative of a linear function, I just get a. The b term vanishes to 0. The ax term becomes a. And crucially, you can see that is a constant. So dp by dt is supposed to equal a constant when I want p of t to be a linear function. That only happens in one of these answer choices. Let's say dp by dt equals 200. Every other answer choice has a variable appearing in it, so it can't be what we're looking for. Done. All right, problem 24, last problem of the video. Now here we're given a function where there's a dependence upon a parameter value k, and we want to pick the value of k that makes the function have some property. Namely, that there's a critical point at some x value, x equals 2/3. The AP loves problems like this, where you're forced to work with a parameter in some sense and force a behavior to happen. You'll see these time and time again. So let's see how to tackle this one. So when we see critical point, I need you to think, that means that g prime is supposed to be 0 or not exist. So let's find an expression for g prime of x and work with it. So using my rule for g of x, we're going to find g prime of x. Now notice this is a product. I have two factors multiplying together, so I'm going to use the product rule. This is going to be the derivative of the first term times the second term plus the derivative of the second term times the first term. Now remember, the derivative of e to the kx, if k isn't 1, we do technically need to use the chain rule and pull that k down as multiplying by a derivative of that inner function. Okay, kind of gloss over that there, but that is what is going on. Because we want to work with this expression algebraically, I'm going to tidy it up a little bit. In particular, I'm going to pull out some common factors. So you can see there's a common factor of x and e to the kx in both terms. What do I leave behind? Well, that first term leaves behind a 2, and that second term leaves behind kx. So this is a nice expression for g prime of x. And in particular, it exists no matter what x or k I pick. So I don't actually need to worry about critical points happening when that expression doesn't exist. So really what we're going to do is we're going to solve for x e to the kx, 2 plus kx equal to 0. Now e to the kx is always going to be positive. So I can just divide both sides by e to the kx to cancel it on the left. When I divide on the right, I still get 0. Okay. So now I have a simple expression being equal to 0. So that tells me that either x is 0 or 2 plus kx equals 0. So no matter what k is, x equals 0 is always going to be a critical point. It's always going to give rise to a critical point. The only freedom that I have in choosing k is what this second critical point occurs at. Okay. So here, let's solve for x. So x is going to be negative 2 over k. And that is the critical point that I can try to make happen at. 2/3. So we're going to set -2 over k, the variable version of the x value, 2/3, and set it equal to the actual value, 2/3, and now I can solve for k. If I just cross multiply, I'll get -6 equals 2k, so k is going to be -3, answer A. And that's that. So how did you get on? Let me know in the comments, particularly that tricky one, problem 20. I'd love to hear from you. If you haven't seen my videos up to this point where I do the earlier problems, I'll put a link to them here. And I've got one more video coming of non-calculator problems from the multiple choice from the 2012 exam. I'll link here.